The broadcast is now starting. All attendees are in listen-only mode.
Welcome to today's webinar entitled AI Can Beat COVID-19 and Improve Energy Efficiencies. My name is Billy Zadig, Manager of Special Projects for APA. Just a couple of housekeeping items before we get started. The webinar recording will be posted to the APA website later this afternoon. Please visit the APA website for archived webinars that are available to everyone for continuing education credits recognized by local, state, and federal professional entities. Professional continuing education and AIA-CLU certificates are being offered for today's program. If you are an AIA professional, please send an email to me at Billie, B-I-L-L-I-E, at APA.org, along with your AIA membership number if you've not done so in the past. Those who indicated they wanted a certificate at registration and meet the requirements will receive certificates later this afternoon. All attendees are in listen-only mode. Please type your questions in the chat box and they will be answered in the order they are received. If we run out of time and we still have questions, responses will be sent directly to the person asking the question by our presenter. If you're just calling in, make sure you send me an email at billie@apa.org so I can send you a certificate if you requested one. The system only recognizes you if you log in. I will rejoin you for the Q&A session. At this time, it's my pleasure to turn this over to Jesse Kraft. Jesse, take it away.
All right, thank you, Billie, and good morning, everyone. My name is Jesse Kraft. I am the Director of Demand-Side Energy Solutions for Siemens Smart Infrastructure. And today I'm going to be talking about how we are leveraging AI to help us tackle challenges with our HVAC systems, both in general with optimization, as well as specifically to COVID and the indoor environment. So let's dive right into it. And the first place I want to start is by explaining a little bit about how HVAC systems are controlled today and why we are going to start leveraging machine learning and AI strategies to help us optimize the performance of these systems. So the first thing to understand when we talk about HVAC controls is that they are built to last on the lifespan of a building. And what that means is there are things that the current HVAC controls that we all have in our buildings, there are certain things they're really good at. They last forever. You know, we have technology that's controlling buildings that's over 20, 25 years old, which is kind of unheard of for the fast pace of technology change today. They're highly reliable and they're really good at the basics. You know, your HVAC control system is like a reliable old pickup truck. You know, nothing flashy, but it'll get you where you're going and it'll run forever. That means that it has some weaknesses. So when we start really trying to fine tune and optimize our building systems, we start outstripping the capabilities of our traditional HVAC controls. So the key areas in which traditional controls struggle with optimization are these four that I've listed here. I'm going to talk about each one of them individually, but these four challenges of optimization that we want to address are forward prediction, meaning not reacting to error, but anticipating error and getting out ahead of it. Non-linear problems, which create very complex optimization problems to solve that are just too complex for traditional controls. Fault tolerance and detection, you know, what do we do when the feedback that we're getting for our optimization is no good? And then the last, which we'll start pivoting into this COVID conversation, is flexibility. You know, what does it mean to optimize the system? So let's talk through each of these, starting with forward prediction. I'm going to use an example of room temperature control to explain what we mean. So here we are, we're looking at this chart of the temperature in a room modulating around set point. And room temperature in our systems are controlled by delivering conditioned air. So if it's getting too hot, we deliver more air. If it's getting too cold, then we drop our airflow. And this type of control, which is very common in our buildings, is always reactive. And what that means is we don't start increasing or decreasing cooling until a deviation from set point has occurred. there is absolutely no ability to forecast that an error might be about to occur. So here's an example of what forward prediction could do for us. So we're moving along, controlling our room temperature, but there's this forecast of a cold front coming through. So, the kind of thing that I would do in my house is I only have heat in my house. If I know it's going to be a cold day, I might turn the heat on in the morning. But if I know it's going to be a hot day, then I might not turn the heat on, even if I'm a little cold at that moment, because I know the house is going to warm up. This is, very basic type things that our systems don't do. So what happens when that cold front comes through is we get this increase in load and the temperature drops. We get hot calls, or cold, in this case, we get cold calls, and it takes, a while for the system to respond and get us back within the control region that we want to be in, all because we were unable to react to something that was very predictable that was going to occur. So ideally, what this would look like is that our system would change its set point in anticipation of that cold front coming through, not just waiting for it to get too cold. It would preheat the space slightly so that when that increase in load does occur, we stay within our comfort band. And that way we're able to, it saves some energy, but it also helps us stay in compliance with comfort, which is a capability that our systems largely don't have today. The next challenge of optimization is nonlinear problems. And I'm going to use the temperature provided by the air handler as an example of a nonlinear optimization problem. So what I'm showing here is this U-shaped curve of a chart. And what this chart is illustrating is how energy is consumed in a typical VAV, or variable air volume cooling system, which is a very common design here in the US. So if I change my supply air temperature of my air handler and I make it too warm, meaning I'm on the very right-hand side of this chart, then what happens is I'm using more fan energy to deliver more air to my space. Because if the air is too warm, it's very ineffective at delivering cooling, so I need more of it. So what happens is I use more fan energy. So we say, aha, let's reduce that supply air temperature, make my air a more effective medium of cooling, and then I will use less fan energy. And as we move on this chart from right to left, that's exactly what starts happening. However, if I move my temperature too far to the left, I now reach this situation where my airflow won't drop any further because I have to provide a certain amount of minimum ventilation into my buildings for the occupants. And we use the same system to control the temperature as well as to provide that ventilation. So as a result, I'm no longer going to save fan energy. And as I continue making the air colder and colder, I'm going to make the room colder and colder. And in order to compensate, my heat will turn on in the spaces. It's very common to go into buildings in the summer and find the heat on, or to go into buildings and be very, very cold, even though it's very hot out, because we're overcooling the spaces. We have not optimized this. This has actually been a much larger problem in the last 18 months as we have significantly reduced the occupancy in our buildings. Many building operators are finding that it's very difficult now to maintain a comfortable temperature because it's too cold. We no longer have all those people and their activities warming up the space, and we didn't equip those core parts of our building with heating, so it's just really cold in there all the time. So anytime we have this situation where trade-offs are occurring between two or more components, this nonlinear behavior occurs. So if I'm trying to optimize my set point, do I raise it to save energy or lower it? It's very difficult to actually determine that answer. So the next one we're going to talk about, the next challenge, is fault tolerance and detection. And I'm going to use an example of an air handler static pressure control. to illustrate this. So static pressure is how we modulate the amount of airflow in a variable air volume system. So as each of the individual room controllers, which are maintaining the temperature in each of the different occupied spaces, they're modulating the airflow based on whether or not it's too hot or too cold. So that modulation of that damper, in order for the airflow to actually drop, we also send a signal back to the air handler via the pressure in that duct. As the dampers close off, the pressure increases, so the fan knows to back off. But what we're doing here is we're operating a building with the way I would describe it is like I'm driving a car and I want to make sure that my car is able to go 70 miles an hour. So I know sometimes I'm going to have to go 70, so I fix the gas pedal far enough down that I know I can get to 70 miles an hour. But I'm in a situation where I only want to go 40 miles an hour. So instead of letting up on the gas, what I do is I press the brake at the same time. Obviously not an efficient way to operate a system, but it's a very common way that we do operate our building systems, where one component will be pushing and then another component will be restricting that flow. And then you have this wasted energy as a result. So ideally what we'd like to do is create a system where we can effectively communicate between the producer of the energy and the consumer and use system feedback to do so. So in this example, what I want to do is I want to figure out how much I can reduce the static pressure that the air handler is generating without starving the boxes that are using that air. So the logical way that this is commonly done is using feedback from the dampers to determine whether or not I can reduce my static pressure. So if all of the dampers are cut back, I know that that pressure can be dropped without starving any of the boxes. This is called trim and respond. It's an industry standard approach, but anyone who has tried to implement it knows that you quickly run into issues. The issues that we're running into here are issues of fault tolerance. So when that damper is going to 100%, is it actually going to 100%, or do I just have an actuator that's broken? Do I have an airflow measurement that is not accurate, that is causing the damper to behave incorrectly? Do I have some external load from, the coffee machine is the classic example, or maybe the temperature sensor for that room is in the sun and gets direct sunlight and thinks it's heating up in the afternoon? How does a system deal with using feedback when that feedback cannot be trusted? So this is something that machine learning is really good at, is determining when feedback is reliable. Now, what that means is not only can we reliably optimize the system with that faulty feedback, but when we detect that the feedback is faulty, that information can be communicated to building operators to indicate that there is a problem. So, what we're doing now with these machine learning algorithms is we're tracking these key performance indicators, these KPIs, like temperature compliance, and we can report on how well we are complying with temperature, which is the goal of operating the system. We can also indicate the likelihood that a zone has gone rogue, meaning that there's a problem with the ductwork design, with the actuators aren't working, with the type of load that we're trying to fix in that system. And we can correct those issues when those wild hairs stick up within the system. We can pair this sort of fuzzy logic of a system's not working right with traditional fault detection to make a better root cause diagnosis of problems when faults are detected. So this is an opportunity to not only optimize the actual control, but also optimize our maintenance practices. Now, the last challenge is flexibility. So we say optimization, but what does optimization mean? When we look at the priorities of optimizing the HVAC system, the top one is always maintaining the indoor environment, right? So this typically means temperature. It would be very energy efficient to just turn the air conditioning off. That would use a lot less energy, but then we wouldn't be maintaining the indoor environment, right? So we always define efficiency as meeting the requirements of the space with the minimum amount of energy input. We also have to satisfy code requirements. You know, there might be times when we could just shut the airflow off, and that would still allow us to maintain the indoor environment because it's a very moderate temperature outside. But we still maintain airflow because that's part of meeting these code requirements. So energy efficiency is always below these two priorities. Flexibility is adapting to a situation where my priorities for maintaining the indoor environment have changed. So this is traditionally met comfort, which I'll call standard operation. So we're maintaining the indoor environment at a desired temperature set point, and in some locations that also means humidity control. But now, in response to COVID, we understand that the HVAC system plays a huge role in how likely an airborne virus will transmit from person to person. So now we have these occupant health requirements, and these could be in a non-epidemic environment, just complying with well building standards, right? Providing enough fresh air, providing enough clean air to promote healthiness in the building. But we also have recommendations from ASHRAE and CDC on how we should be operating our HVAC systems in response to an airborne epidemic. Air quality is also a huge issue. I live out here in California, and I used to look forward to summers, but now summer means wildfire season. And we get these days where the air quality is incredibly poor and you really can't go outside. So you definitely don't want to bring that outside inside if you can avoid it. So how do we change how we control our HVAC systems in response to air quality issues? So all of these have to be considered by the optimization algorithm and understand what the operators are trying to achieve. I'm going to take a moment here to explain in a little more detail how the HVAC system and its operation actually impacts virus transmission within a building. We have essentially three mechanisms by which virus can be removed when it's brought in by an infected individual. The first is deactivation, right? For lack of a better word, killing the virus. This is, in some ways, the most satisfying way to tackle the virus, but it is not necessarily the most effective. Much more important are suspension and dilution. So not just waiting for the virus to die, but can we just physically remove it from the space by bringing in fresh air? And then suspension is, can we remove the virus from the air and get it to filter down to a surface so that it's less likely to be inhaled by other individuals? One way to think about these three mechanisms is think about your own personal infection controls, right? What are those? Those are washing your hands, socially distancing, and wearing a mask. So if you were washing your hands, and we might remember that some early advice was to sing happy birthday twice to ourselves while we washed our hands. What we were trying to do is deactivate the virus that might have been on our skin. Suspension, keeping the virus from floating around, that's wearing a mask, right? When we breathe out, if we are sick, then the virus is hitching a ride on our respiratory particles. Wearing a mask reduces the concentration of those particles. as also when we breathe in, it does the same. And then dilution is social distancing, right? Reducing the concentration by there being fewer people present. Filtration and bringing in outdoor air have a similar impact on the likelihood of transmission. Right, so deactivation, we understand that a virus is not technically alive, so we can't technically kill it, so we use this word deactivation. There's not a bright line of conditions that kill a virus. This is why, when you look at your hand soap, it says it kills 99.9% of germs, because what they're doing is they're doing some, math on this exponential decay line. You can look at how temperature and humidity, in addition to things like chemicals and ultraviolet, change the rate of deactivation of COVID-19 specifically. The Department of Homeland Security has created a calculator that you can see how it impacts the timescale of deactivation. So suspension is primarily driven by humidity. There's been a lot of research related to influenza, another airborne illness, that shows that 40 to 60% indoor humidity is this kind of sweet spot for reducing the concentration of virus in the air. When humidity is very, very low, when you can see your breath when you breathe out, what you're seeing are those respiratory particles. And when it's visible, what's happening is it's turning into an aerosol, and it's going to stay suspended for a really long time and therefore be more likely to be inhaled by someone else. Medium humidity is key. You have that less of a tendency to evaporate. Now, higher humidity would be better, except it causes the risk of other issues within the building when humidity gets too high. So indoors, 40 to 60% is our sweet spot. And then the last one, dilution. We've got this contaminated room air, and we can replace it with fresh air. Another mechanism available to us instead of, or in addition to, more outside air is increased filtration. So a lot of folks have upgraded their systems to MERV 13 filters, and what ASHRAE has said is that a MERV 13 filter is just as good as going to 100% outdoor air. It essentially removes the same amount of virus. Now, not everybody can go to MERV 13 filters because that additional pressure drop on our systems might take us outside of our design guidelines. So if we can, then that's great. If we can't, then outside air would be another way that we can achieve that dilution of any virus that's being shed within our occupied spaces. Now, this is all just the guidance on what we should do, but then how do we turn this into action? What do I focus on? What do I actually change about how my building is operating? So there's a balance that goes on, right? I want to bring in outside air, but what if it's winter out and I'm having a huge cold snap, which is kind of relevant right now? I can't bring in 100% outdoor air because that's going to drop my humidity in my building. It's going to drop my temperature. In fact, I might not even be able to keep up with the load with my heating system if I go to 100% outdoor air and it's, 0 degrees outside. The same situation in reverse can happen in the summer, right? If I go to 100% outdoor air and it's, 80 degrees with 90% humidity, then my cooling system won't be able to keep up and I'll start losing control of the humidity within the building. So there has to be this balance that occurs. I also might not always need to be in this COVID sequence of operations, right? So how do I change between that and a traditional optimization? And then, the guidance has become relatively steady at this point. early on in the pandemic, the advice on how to operate our HVAC systems was changing quite a bit. And we had some customers that really struggled because they were implementing changes to their system only to find that those recommendations were outdated and they needed to change what they were doing. Now, perhaps that will happen not because we're learning more, but because the response of the virus changes, or a different pathogen becomes relevant and different balance is required. So how do I have a system that can adapt to different requirements without needing to constantly reprogram my own system on site? So all these challenges of optimization, where do they lead us? They lead us to this idea of cloud-based AI optimization. So doing it cloud-based has a lot of benefits. Lower cost, right? Typically, the equipment that we're installing on site is not capable of handling this level of computation. So I might need to spend thousands of dollars on additional equipment, additional computing equipment. It also simplifies site operations and updates. We're not gonna have as many experts on AI as we do on traditional HVAC controls. I mean, we as an industry, that's likely not going to happen. So when something needs to be serviced on site, that can take time to do, versus cloud optimization allows for access to that algorithm by the relevant experts without needing to get on site or even to access your network, right? They can do that all above site. And then it also enables data connections. If you want to do forecasting, you have to have access to forecast data and weather data. Community health data or air quality data can all be used to inform the algorithm without needing to install sensors for all that information on site. Now, the weakness, of course, is that there are some network security risks. Now, I don't want to completely blame Target for the fact that we have customers that don't want to install cloud-based solutions, but it is Target's fault. So I'm sorry if someone from Target is on the call, but this is your fault. So what did they do wrong? So other than just allowing a cloud connection. So you should have, and this is just good cybersecurity practice, right? Your BMS network should be isolated from your business critical infrastructure. There's no reason to run those on the same network, on the same servers. Use VPN tunnels, right? So it's not possible to penetrate that connection from outside a secure connection on the other side. And then don't use default passwords. Again, that one seems really obvious, and yet this is how the hackers broke in through the HVAC company. So we have a lot of documentation on how this should work. We do a lot of, we have cybersecurity experts, have learned a lot since 2014. I would encourage you to not be scared of the cloud just because some people have done it wrong in the past. This is the future, and we do need to embrace that and work with our IT teams to come up with solutions that work. So we get into the cloud. So what are the benefits of doing so? So we talked about simplifying the updates, right? And we do this with our personal devices all the time. There's an update for my iPhone. I don't need to go to the Apple store or have a technician come out to my house to reprogram it. It all just downloads from the cloud. So we're definitely familiar with these benefits. It also enables data connections. So I have this cloud or this AI engine sitting above site that interfaces with the BMS controls on site, and it also has the ability to interface with external information. So think about all the ways you could improve the performance of an optimization algorithm: weather forecasting, air quality data, real-time energy pricing, right? All of this could inform an optimization model. So the way a typical cloud-based optimization architecture is going to work, you're going to have DDC or direct digital controls down to the zone level. So if you have an older building that still has some pneumatics or some pneumatic controls, controlling the spaces, that would need to be upgraded. These are also all using BACnet communication protocols, which is the industry standard. So if you have an old proprietary system, you will likely need to make some sort of upgrades or some sort of allowance for converting that into a BACnet signal so that it can be communicated. Otherwise, these systems are all BMS agnostic, and system architectures are flexible. So you can, depending on the criticality of your system, you can use kind of the standard approach, which is highly secure, using an IPsec tunnel between the cloud and the local BMS network. Or you could also provision for additional security between that VPN endpoint gateway and the local BMS network with a customer provision firewall or DMZ. So let's talk about some results of this approach. So first, let's look at energy impact. The type of results that we see from optimizing a system, they do vary pretty greatly depending on the existing condition. There's really one major variable though, which is whether or not some level of optimization through traditional trim and respond approaches has been attempted and whether or not that is working well. So if you have reasonably good trim and respond algorithms working, then this approach should improve the efficiency of your HVAC systems overall by 8 to 15%. That's kind of the range of outcomes that we've seen. If there are no existing resets in place, then the savings are higher and also the window of savings is a little larger. So we've seen from 20 to 35%. So what you're seeing on this pie chart is a single building where we optimized the five air handlers. Two of them did not have existing resets. So you can see air handler 4A and 1D that take up a bigger part of the pie to begin with. There was no existing resets on those. And then the other three did have some existing resets in place. You can see there were still pretty significant savings across the board. So overall, like this blended project saved about 20% on the HVAC cost for this building. The other impact is a comfort impact. So what we expect to see is that by using this AI control, which is directly reading the temperature of the spaces, that we are going to be able to get tighter control on the temperature within the zones. Now, it doesn't address every temperature control issue. You're going to have some spaces that just have, too many windows, the load has changed. There will be other things than the control strategy that will impact the temperature compliance. But what we generally see is either we maintain or even improve temperature compliance within the occupied space. So let's talk about a couple of specific customer sites. So the first one is one of our earliest projects. This was 1111 Broadway in Oakland, California, where we saw improved document comfort and energy efficiency and also provided the benefits of defense mode. So this site saw 15% reduction in building HVAC energy costs. And we saw this was the building that had the temperature compliance from the previous chart. We saw a reduction of about 40%. This was implemented prior to the pandemic. We then went back and were able to implement the additional operating modes to support occupant health after the fact, as well as using the diagnostic data from the system in the building maintenance planning. Maybe a little more relevant to some of the folks on the call today is this case study from a K through 12 customer. This is the Northwest Catholic District School Board. This is in Ontario, Canada. I might be forgetting which province it's in. I apologize to Canada. So here we did a combined project of building commissioning and machine learning optimization to improve ventilation. So one thing I didn't spend a lot of time talking about today, but I think should definitely be mentioned, is that optimization relies on properly functioning HVAC infrastructure. So for many customers, before we do this, we will go through a building commissioning process to make sure, are your dampers working? Are your valves working? Are your temperatures working? Which in the past, some of these things might have been let go because there was minimal energy impact or things, it wasn't worth the investment. But when we're talking about implementing these COVID mitigation strategies, you now need to treat your comfort cooling systems or your comfort systems the same way you would treat a life safety system. That outside air damper that's been stuck that we didn't bother with because we either weren't aware it wasn't working or the impact wasn't that negative. Well, now that becomes crucial to controlling our outdoor air percentages. So we need to fix that issue. So what we did here is we commissioned the system, we implemented DVO, which actually cost less than trying to program a custom built solution to implement these things within the building automation system. The custodial staff and the maintenance staff, they had been manually changing outdoor air percentages. I expect some customers are still doing this, which is because we know we can't always go to 100% outdoor air. We are changing the percentage of outdoor air manually each day or even throughout the day in order to keep the building safe and also make sure that we can retain control of it. So they had been doing that at these schools, and they now no longer need to do that because the system is controlling it. They were also able to leverage COVID relief funding. So many customers still have funding available to upgrade their infrastructure in response to COVID. And these sorts of upgrades, fixing your HVAC system, upgrading your building automation system, your HVAC components, all of this is absolutely eligible for that funding source. And then the last is, because the same machine learning algorithm has this optimization for building health and also for energy efficiency, after the pandemic, at literally the push of a virtual button, they will be able to switch into an energy efficient mode of operation with no additional investment in the system, no additional programming, no additional cost. It's already there waiting for them to use it. So those are the slides for today. I think we're ready for the question and answers, or the questions anyway.
Thank you, Jesse. We have a question here for you.
Okay.
In addition to what you've discussed today, what other solutions can help our campuses meet ASHRAE and CDC guidelines?
So one thing I did touch on a little bit, but I want to make sure to emphasize it, is building commissioning. So one of the important things that we can be doing with our HVAC systems, if we haven't done it already, to make sure that we're bringing in the appropriate amount of air and controlling temperature and humidity properly, is to be recommissioning those systems with that mindset of this is now a critical life safety system as opposed to simply a comfort cooling system. If you haven't investigated MERV 13 filtration yet, I would strongly recommend that you do so. Understand if your systems are capable of handling the additional pressure drop that those more heavy duty filters will impose. But that is another great step that building operators can take to improve the ventilation within their spaces. If you haven't done any investigation into improving ventilation, whether it's this type of solution or something custom programmed, It was slightly controversial at the start of the pandemic, but it no longer is. COVID is transferred via person-to-person transmission. It is airborne. As such, the ventilation in our buildings is absolutely critical to improve if we want to make our buildings a safer place to be.
Well, thank you. Okay. Our next question is, how can I integrate subscription paid online weather forecasting APIs with your PXC controllers?
It's a very specific question, which I appreciate. So this is a question specifically about the Siemens building automation system. Without getting into too much of the details, I will say that the front end of what we call the Zico CC, which is our front end, or almost any modern building automation front end is capable of integrating with web sources through either APIs or other types of communication protocols. So what I would do is I would contact your local Siemens rep, or if you don't have one, I'm going to put my contact information here on the slide. So there's my email address. And yeah, you could definitely get there are definitely solutions for that sort of approach.
Okay, thank you. Our next question is, if an air handling system cannot handle MERV 13, can portable HEPA filtration be integrated into AI systems?
So the short answer is yes, and the way that I'll try not to get too much in the weeds here. The way that the filtration level gets integrated into the AI system is you tell the AI certain facts about the building. What kind of level of filtration do you have? What's the area? What's the volume of the space that we're dealing with? And also you tell it things like, are we still socially distancing in this building? Are we still wearing masks in this building? Because that sort of information about personal controls also informs the level of ventilation, temperature, and humidity that is recommended, where that balance will reside. So whether that filtration is being done through the central HVAC system or whether it's being done through a portable, in-room filter, knowing that information about the level of filtration is one of the inputs to the algorithm.
Okay. Our next question is, in older buildings, would MERV 13 filter reduce the amount of OA, therefore reducing the dilution rate?
Well, in any building, if you put in MERV 13 filters on a system that wasn't designed for it, two things are going to happen. So the first is that you're going to have lower overall ventilation capacity, because that fan is now going to use more of its energy overcoming the pressure drop instead of moving air. So that is one thing to consider, is whether or not adding that MERV 13 filter will restrict your airflow too much. But when we're talking about dilution, MERV 13 filter, recycled air through a MERV 13 filter and outside air, ASHRAE has said consider those equivalent. So it's not going to, it allows you to reduce your outside air. So that's a benefit, not a downside of the MERV 13.
Okay, well, that's all of the questions that we have. Oh, I just had one come in. Yes, copy of the presentation will be available. Jesse will send it over to me later this afternoon. When you get your follow-up email, just respond to it and let me know, and I'll send you the presentation slides. Other than that, I think we are. Oh, another question just came in. Your approach refers to a reprogramming application to optimize HVAC controls. Does this approach include the integration of other sources of factors influencing control performance? Do the optimizations integrate boilers, lighting controls, to mention in the development of appropriate control algorithms?
That's a great question. I think that would be a good topic for another webinar because it's a pretty in-depth answer. The short answer is that we can. So what we do is, in optimizing the energy efficiency of a system, you need to know something about the efficiency of the source of heating and cooling, and you can do that as simply a fixed assumed value, which we would do for some simpler systems. But if you have implemented, chiller plant optimization or boiler optimization, where the efficiency of that system is going to be varying, that's an additional input that you can integrate for it when it's making those optimization decisions.
Okay.
I would also just add. No, sure. I would also just add that these algorithms are going to continue to evolve and get better at optimizing. So we're going to continue, making changes to pick up the remaining nickels, dimes, and quarters that we haven't caught yet. We've probably caught all the paper money at this point that we can. So that's another benefit of the cloud-based type of solution, is that as the algorithm continues to improve, continues to develop, those upgrades get automatically deployed to your site without needing to make any changes to your on-site programming.
Okay. Our next one is, one of the concerns I've had with standalone room filtration systems is that the possibility of short-circuiting the airflow. In other words, how do you ensure that all the room air is actually being run through the unit to be filtered?
I think that's a great question for the manufacturer of a room filtration system. I'm not nearly as versed on the intricacies of designing and appropriately selecting those systems. I think it's definitely a good question, though. I'm just afraid I'm not really able to answer it.
That's okay, Jesse. We appreciate that you are honest with us. And one other question that just came in is, have you heard of Crystal Clean Air?
No, but it sounds great. Love the name.
Okay. Well, that is the end of our questions. So, Jesse, I'd like to thank you for a very informative presentation today. And to our attendees, thank you for taking time out of your busy schedule to be with us. So until next time, be safe, stay healthy, and have a great weekend. Bye-bye now.